Hello and welcome back to Data Analysis and Visualization. I'm Jivita Christie, and in this video, I'm going to talk about random variables and probability distributions. Let's begin. What you see on your screen here is a roulette wheel where people can place bets about, when the wheel is rotated, then where exactly the ball would land. Would it be on a black number or a red number or a green number? So they place bets and then they can win if the ball actually lands on that particular color. So in this, when you turn the roulette wheel, you intuitively understand that there is an equal chance that the ball will fall into any of the slots of the cylinder on the wheel, because there are about 38 slots, I think, and there's equal chance of the ball falling on any of those. The slot where the ball will land is totally random, and the probability or likelihood of the ball landing in any one slot over another is going to be the same. Since the ball could land in any slot with equal probability, there is an equal probability distribution, which is also known as a uniform probability distribution. And you'll learn a little bit more about it as I proceed with this video and explain to you some probability distributions. But in general, uniform probability distribution means the ball has an equal probability of landing in any of the slots in the cylinder. But the slots of the roulette wheel are not all the same, because you have 18 black slots and 20 slots that are either red or green. So there are totally 38 slots, but out of those 18 are black and there are 20 which are either red or green. And because of this, the probability that your ball will land on a black slot is 18 by 38. And so naturally, you plan to make successive bets that the ball will land on a black slot. So when you're making successive bets, that means you want to play the game maybe 5 times or 6 times in a row and see how many of those times the ball actually lands on a black slot. So that would be successive bets, and your net winnings can be considered a random variable here. Because if you're playing 6 times, then what are the total times out of those 6 where you're winning and how much money you're getting? So a random variable is a measure of a trial or value associated with an object, a person, or a place, something in the real world that is unpredictable. So random variables are unpredictable. Because this trait or value is unpredictable, it doesn't mean that you know nothing about it. And what's more, you can use what you do know about this thing to help you in your decision making. And we're going to see that now. So we'll begin with weighted average. What is a weighted average? A weighted average is an average value of a measure over a very large number of data points. If you take a weighted average of your winnings, that means your random variable, across the probability distribution, this would yield an expectation value or an expected value for your net winnings over a successive number of bets. An expectation can also be thought of as the best guess if you had to guess. So the weighted average in general is the average value of a measure over a large number of data points, which means you're going to try to rotate this roulette wheel and see what is your weighted average. So if you take a weighted average of your winnings, that means how many times you won out of all those number of times you played across a probability distribution, then you would get an expected value, because now you have so many experimentation results. When you have so many results, you're able to make a better guess about how that actually works out. What is expectation? To describe it more formally, an expectation is a weighted average of some measure associated with a random variable. If your goal is to model an unpredictable variable so that you can make data-informed decisions based on what you know about its probability in a population. You can use random variables and probability distributions to do this. So expectation is all about finding out what is the weighted average, and then based on weighted average, finding how you can make your unpredictable variable more predictable, because now you know something about it, and that could help you in predicting something about this unpredictable variable. Now we're going to proceed with probability distributions. So imagine yourself walking down the sidewalk and observing the eye color of people you see. You notice that some people have brown eyes, some have green eyes, and so forth. In all honesty, you have no idea what the eye color will be of the next person you see, but you do know that blue and brown seem to be the most common. And because you've observed this, you can make a somewhat educated guess about the eye color of the next person you see in the scenario, the next person you see. And in this scenario, the random variable that we're discussing is the eye color. So your guess as to what the next person's eye color will be is based on what you've learned so far about the probability distribution of people's eye colors on the sidewalk. So because you have seen so many people on the sidewalk having either a blue or a green eye color, that is why you can now make an educated guess that maybe the person who comes up next is more likely to have this particular eye color because you've already seen some data about it. Now imagine that you actually sat down and recorded counts of what you've observed of people's eye colors. And observations counts show you, those observation counts show you that 35% of the population is having brown eyes, 30% is having blue eyes, 10% amber eyes, and 10% green eyes, 5% violet, and 10% gray. So this is what you found out because you sat down there and started counting the number of people with this many, with the eye colors, different eye colors, and you found out that this is the percentage of people having eye colors of this kind. So these percentiles that you got are in fact the probability distribution because they tell you the exact probability of eye color distributed across the population. These percentiles represent a probability distribution, and the expectation in this example would be the average number of people having any one eye color. So average number of people having any one eye color would be the expectation. Now, probability distributions are classified according to the two following types. The first type is discrete distribution, which is a random variable of which values can be counted, for example, eye color. And another one is a continuous distribution, which is a random variable that assigns probabilities to ranges of values. For example, if I'm going about seeing different students in my class and I want to create a probability distribution based on the marks that they are getting, then I wouldn't be doing a discrete distribution because it doesn't make sense. If marks are out of 100, am I going to count how many got 1 mark, how many got 2 marks, how many got 3 marks? That doesn't make sense. So in that case, I would be going with a continuous distribution where I would be assigning ranges. How many students got marks between 1 and 10? How many got between 10 and 20, 20 and 30? That makes more sense. So that would be continuous distribution. And based on that, we have different types of probability distributions, and we're going to see them now. The first one is uniform distributions. If you remember, I talked a little bit about these distributions in the beginning of the video. So these distributions are used to distribute probability equally over all possible outcomes. So they are discrete, and if it's not discrete, then you can distribute it equally across ranges of outcomes, so continuous. This distribution is especially useful in virtual experiments or simulations to explore real-world phenomena. So it could be like the experiment where you are rotating the roulette wheel couple of times to find out what is the outcome each time. So that is one thing. You could rotate the roulette wheel a couple of times, find out what is the outcome each time. And so that's an experiment, a virtual experiment or a simulation that you are running. And that's an example of a uniform distribution. Because it is a uniform distribution because every slot has equal probability of being picked. The next type of distribution is binomial distribution. This will model the number of successes that can occur in a certain number of attempts when only two outcomes are possible. So it's the old heads or tails coin flip scenario, for example. So binomial distributions, as the name suggests, they work on binary values. So if you have a coin, you're flipping it, and you want to see whether you get a heads or tails, the probability of getting either heads or tails, then this is binomial distribution because there are only two outcomes. So there are a number of attempts, but only two outcomes are possible. That would be binomial distribution. Next is geometric distributions. These distributions you can use to give the probability of such and such number of attempts occurring before you're blessed with your first success. A very good example of this is if someone is considering having a baby and they want to have a boy, then a geometric distribution could tell them how many children they need to have a high probability of having a male child. So this is something that, there is an experiment, but how many times do you need to do this experiment to have a success? So that is geometric distribution. Next is hypergeometric distribution, which is a variant of geometric distribution model, and it gives you the probability that some number from a sample will be of a particular value. Probability of, say, drawing a female from a set of males and females, for example. So if you had, say, 10 males and 10 females, what would be the probability of picking one female out of that group? That is hypergeometric distribution. In hypergeometric distributions, there are no replacements when samples are taken from a finite population. So if you studied probability before, you would know, and if you even studied permutations and combinations, you would know what it means to have replacement and no replacement, which means once you pick something for calculating probability or permutations or combinations, you are not going to put that thing back again and pick another one. Once you pick one, then that remains out, and then you pick the second one, third one, fourth one. So that is hypergeometric distribution. And as samples are drawn, the size of the remaining population decreases, and the probability of drawing a male or female sample changes based on the net decrease in the population size, which is quite logical because if you have, say, 20 people and you're drawing one person out from there and you're not putting that person back in the group, then the number of people is going to reduce. And because of that, the next time you want to find out the probability of picking a female out of that group, now you're dealing with not 20 people, but 19 people. So the probability calculation is going to essentially change. The next distribution that we're going to study is the Poisson distribution. So the Poisson or discrete exponential continuous distributions complement one another. So there are two of these kind. Poisson is for discrete and exponential is for continuous. Say that there is an intersection in your town that has a lot of accidents. So this is an example. I'm going to explain it further, but consider that there is an intersection somewhere in your village, in your town or city where a lot of accidents are happening. Okay, so now here, a Poisson distribution answers the question, what is the probability that such and such number of accidents will occur there within a week? So within a week, how many accidents will occur there? What is the probability that, say, 10 accidents will occur there? That is Poisson distribution. But exponential distribution would answer the question, what is the probability that the time until the next accident is such and such length of time? So what is the probability that, the next accident will occur in the next 10 hours? That is exponential distribution. So these are the two distributions that complement each other, and that's why they are put together in the Poisson distributions. Next, we have normal distributions, which are very interesting. These distributions model phenomena that tend toward some most likely value, the top of the bell in the bell curve, with values at the two extremes becoming less likely. So you can see here, this is the bell-shaped curve that is created if you were to plot a normal distribution probability. Then this is the type of curve that would be created on your graph. And you can see it is a bell-shaped curve. And the points that lie on the top of the curve, those are the points where the probability is the highest. And then as you keep moving outwards, the probability becomes lesser and lesser. So events that are outward on the curve are extremely less likely to occur compared to the ones that are on top of the curve. So this distribution is a very interesting one, and oftentimes the one that is asked in exams. Next, we have gamma distributions. So you have to plan for all possibilities, even the possibility that no pattern exists. So far, we've seen distributions with patterns, patterns about how many accidents will happen, or at what time by what time the next accident is going to happen, and probability, binomial probability, two outcomes. So there are patterns, but you have to be prepared for a situation when there is no pattern, and that's where gamma distributions do precisely that by allowing for non-symmetric distributions. Gamma distribution, which is continuous distribution, assigns probabilities to random variables. In gamma distributions, gamma distribution plots probabilities never have negative values, and they never fall within a range of values. And they fall within a range of values between 0 and 1, which is true for all probability values. But for gamma distribution, the plot that you make, the graph that you make, is not going to be necessarily symmetric. It could be non-symmetric, and you may find no pattern in it. That's where gamma distributions will do their work. The gamma distribution is useful in modeling time to failure, a method that's useful for predicting when a device is most likely to fail based on observational data and probability distributions. And finally, we've got beta distributions. So this is the most versatile player on the distributions team. They are structured so that they can be made to fit almost any pattern as needed. So beta distributions are even more different, are more linear, or more liberal than gamma distributions, because there is no pattern at all here, and they can fit into any pattern that you want them to fit into. So these are all the distributions that are there when you study probability. And I hope you understood all those distributions, and I'll be back with the next video, and we'll talk more about statistics there. So see you in the next video. Thank you for watching.